So with that, let's move on to the third session of the symposium, which is the first session of today, entitled Methodological Advances in Phylogenomics. And it is my pleasure to introduce our first speaker, Xiaofan Zhou from South China Agricultural University, who is going to talk about when the uncertain meets the incomplete, robust measures of phylogenetic incongruence. Thank you, Xiaofan. Feel free to share your screen when you are ready.
Okay. Can you see the screen now?
Not yet.
Interesting.
It says double click to enter full screen mode. There you go.
Oh.
Yeah, all fine.
Okay. Is it okay now? Okay. Thank you. Okay, I will start. First of all, I would like to thank Rosa and Jesus for organizing such a great event and for the invitation. And it's particularly happy. I'm particularly happy that during this special time we can still have the chance to talk about science. So today I would like to talk about an approach we recently developed for measuring the phylogenetic incongruence, particularly for datasets with missing data. So the topic phylogenetic incongruence has been brought up several times in yesterday's talk. But in case that you missed the talk yesterday or you haven't thought about the problem this question before, I will just give you a very brief background introduction. Actually, when we are doing molecular phylogenetics on organismal relationships, a lot of times we are actually looking at the evolutionary history of genes, hoping that they would reflect the history of the species. In the early days, we due to the limitation in data acquisition, we most of the time we only work with one or very few number of genes. But in recent years, due to the rapid development of high-throughput sequencing technologies, we basically are facing a flood of genomic data. No matter you're doing genome sequencing, transcriptome sequencing, or targeted enrichment sequencing, you can very easily get tons of data for the group that you're interested in. So these are just several examples of phylogenomic studies of major clades in the life of tree. So basically we can do like phylogenetics on hundreds of species with hundreds to thousands of genes. So in those studies, it's very easy to see that tree of life have been resolved, but unfortunately, sometimes they can be resolved in different ways. If you have heard the talk yesterday, you will know there are several examples already. But if you didn't, I will give you an interesting one about the early evolution of animals. So it's a really hotly debated topic, and there are several alternative hypotheses. And so the example are coming from two papers that appear almost side by side on PNAS. That's why I think it's quite interesting. And one paper says Ctenophora is the earliest, represents the earliest divergence in the animal phylogeny, but the other says Peripheral. So they're contradicting with each other. Although if you look at the tree themselves, both of them are highly resolved. They receive perfect support for the relationships. And that's common in phylogenetic studies. You get perfect or near perfect support for most of the nodes in the tree. It's probably because we have a lot of data. But if you look at the evolutionary history of the genes in the datasets, it's a completely different story. So here I would give you another example. Is the phylogeny of 23 East from a Nature paper in 2013. And this tree shown here, those asterisks are bootstrap supports. So it means all the nodes here on the tree receive 100% bootstrap support. So it's perfect. But if you look at the gene phylogenies, see how many genes support each of these relationships, the numbers vary greatly. So only a few of them still have 100 support. The others have much lower support gene frequency, support frequency compared to the branch support. And if you compare the phylogenies of the genes versus the species tree, surprisingly, none of the single gene phylogeny is identical to the species phylogeny. And if you compare between those gene trees, none of the gene trees are identical to each other. So they're all different. Means there are a huge amount of phylogenetic incongruence between them. And this single gene support frequency number, unless they're really high, close to 100, or really low, close to 0, otherwise they don't really give you a full picture of the incongruence or the congruence. For example, if you are interested in a question, you have 40 genes. You ask how many genes support the reference tree, how many genes doesn't, and your answer could be 20 versus 20. Okay, but there could be different scenarios behind that. In one case, you could have 20 genes supporting the reference topology, and the other 20 all support a totally different one. Or in another extreme cases, you can have the 20 that disagree with the reference, each support a different hypothesis. Okay, so these are two very different scenarios and different kind of incongruence, and lead to different explanation and downstream analysis of the data. But you cannot tell from one single branch support value. So we need a approach that can conveniently tell us the level of phylogenetic incongruence regarding the relationship that we're interested in. So a few years ago, Leo from the Rokas lab at Vanderbilt developed this approach called Internode Certainty. So the basic idea is that if we are interested in a certain relationship, that will be an internal branch in the tree. So the branch will separate the taxa in the tree into two subsets. So we can ignore the topology within each subset. We're going to identify among the gene trees or evaluation trees, which bipartition induced by the different branches are congruent or incongruent with the bipartition shown in the reference tree. Okay, for example, if I switch the E and F in the reference tree, and I got the gene tree like this, this bipartition in this gene tree will contradict the reference bipartition. But if we are looking at a different branch, for example here, which separates ABC from the others, this switch of the two taxa will not introduce a contradiction to the reference. So for the dataset, we will identify for each of the branches in the reference tree, how many genes will have a conflicting bipartition and how many genes will not, and how many different contradicting bipartitions are there. And we'll basically apply a Shannon's entropy formula to calculate the uncertainty. But since we are interested in the certainty, we will basically take negate and add 1 to get the internode certainty level. So that's a very good way to using just one single number to review the level of phylogenetic conflicts. However, a major limitation of the approach is that it can only apply to datasets with no missing data. So every gene tree in the datasets need to have all the taxa. But that's quite unrealistic in the phylogenetic datasets nowadays, because a lot of times our data coming from like draft assemblies, transcriptome assemblies, we can easily miss a lot of genes in a lot of different species, and the genes can be lost biologically by the organism. So we will have a lot of missing data in the datasets. So to apply this bipartition-based approach onto datasets with missing data, it can be quite complicated. For example, if the reference tree have 5 taxa here, A, B, C, D, E, and in the gene tree, it missed the taxa taxon A and has only B, C, D, E. So this tree topology is congruent with the reference tree. However, if you think about where the A would go, only if the A falls here in the internal branch, this tree topology will be congruent with this reference one. If A falls onto any other branches, it will introduce a conflict with the reference. So we have to think about ways to attribute the frequency of incomplete gene trees to all kinds of potential congruent or incongruent topologies. Fortunately, in 2016, this original Internode Certainty approach have been modified and extended to the incomplete gene trees, but it's still based on bipartition. And there are basically several problems of bipartition-based IC measures. So it can now be applied to datasets with missing data, but there are still several major problems. So first of all, in the extension, they developed two different algorithms to adjust the frequency of partial gene trees to complete gene trees. But in practice, a lot of times these two different approaches, algorithms can give rise to very different scores, and it's not necessarily clear which score is better or should be preferred. So it would be confusing. And in cases where there's very little phylogenetic signal, you would have artificially high IC scores. So for example, if neither the reference topology or either of the conflicting topology is supported, for example, here it's only like 0.1% support, you would still get a IC score of 0.28, which basically is the score you would get from 20% versus 80% versus 20%. Is a quite high certainty score. So that's basically an artifact. And another thing is that the total number of conflicting bipartition you would get from your datasets is not clearly defined. Based on the actual datasets you get, you may have only one conflicting bipartition, or you could have a large number. So that affects the base of the logarithm in the Shannon's entropy formula. So it could affect your calculation of the IC score a lot. So when we think about this, we think the better solution could be to look at this question at the level of Quartet. So Quartet, basically, they are the most basic unit of information for a phylogenetic tree. They're like the sets of 4 taxa. And the good thing about Quartet is that it has a fixed number of alternative topologies. So each quartet, since it has only 4 taxa, so unrooted quartet tree can at most have 3 different topologies. So we have a fixed number of alternatives that we need to consider. And no matter how many taxa are included in the gene tree, we can, in our calculation, we will decompose them all to the level of quartets. So we don't need to adjust the frequency of genes because we are comparing quartet trees. They all have 4 taxa. And also another side advantage is that since small gene trees will give rise to smaller number of quartets, large gene trees will give rise to greater number of quartets. So the number of quartets from a gene tree would naturally reflect their information content. Okay, so that's a good thing. So for the quartet, we can calculate internode certainty for Quartet just like we do for the bipartition. We just need the frequency of each of the 3 alternative topologies, and we can apply the same formula. And the base of the logarithm here will be a fixed number 3. So if we take a look at this toy dataset as an example, this dataset has a reference tree of 6 taxa. and several different evaluation trees. Some are complete and some missed 1 or 2 taxa. And the first thing we would do is to decompose the reference tree into quartets. So since we have 6 taxa, in total, we will get 15 different quartet. And each quartet has 3 different alternative topologies. One is represented in the reference tree, and there are 2 other alternative topologies. So we will basically, first of all, get the occurrence of each of these quartet topologies from the evaluation tree dataset. And then the quartet-based IC measures come in different flavors. So the first one, we call it quadripartition IC, or in short, QPIC. So basically, when we are looking at a given internal branch, the branch will separate the tree into 4 subsets. If we believe the separation of the 4 subsets are correct, we just accept that. It's just like what we do for like the A-base branch support, or the approximate SH branch support. So that's basically a meta-quartet or a quadripartition. Since we have 4 subsets, there will be 3 alternative topologies for this tree with 4 subsets. And we will basically take the quartets that's relevant to each of these 3 quadripartition quartet tree and count their occurrence. For example, here, the quadripartition tree topology from the reference tree will have a total count of 12 from the evaluation tree. And the most prevalent conflicting topology has a count of 24, and the other one has a count of 0. So we can calculate the Internode certainty for this branch, the QPIC, using the same formula here. We will get the IC value of -0.421, means that first of all, there is a certain level of incongruence, and second of all, the most popular prevalent conflicting topology is has a higher support from the evaluation tree than the topology in the reference tree. But the problem here in this QPIC is that only a small fraction of the quartet are considered. If you think about this branch, in QPIC, we're only looking at those 2 internal nodes, the neighboring internal nodes. But if we look at several other pairs of internal nodes, for example, this one, it's also relevant to this internal branch. So any quartet that violates this A, B, C, D topology will directly violate this branch, right? So we extend the QPIC approach to all possible pair of internal nodes in the tree, and we call it extended QPIC. So we basically look at all pairs of internal nodes, and we calculate the QPIC score for each of them. And for the internal branch we're interested in, we just take the minimal QPIC score from all relevant IC scores of the internal node pairs. And in this case, the minimum is still -0.0421, same as the QPIC score.
2 minutes, Xiaofan.
2 minutes.
2
okay,
minutes.
I will finish very shortly. So we use a simulation dataset to test the performance of our approach. First of all, the first thing we did is to compare the IC scores we get from the quartet-based IC measures versus the previous bipartition-based approaches. So it's assuring that we see they are very well correlated. So on complete datasets with no missing data, we're still getting very similar IC scores. But then how does it perform on datasets with missing data and other difficult data conditions? So first, we test the performance on datasets with missing data. So we basically, to create datasets with missing data, we basically take out taxa from the gene trees. And we looked at medium level or high level of gene tree missing data. and we compared the IC scores we calculated from the datasets with missing trees versus the score from the original complete gene trees, which we think represents the ground truth. And we ask like how many of them are overestimated. And you can see that the two Quartet-based IC scores, they are very close to the ground truth compared to the bipartition-based IC scores. And they're very, in only a few cases, they are overestimated. The bipartition-based IC scores are overestimated in a lot of cases, particularly when there's a lot of missing data. And we also looked at two other conditions like the lack of signal. So the Quartet-based IC scores, in the lack of signal, so when the gene trees basically can take any topology, random topology, so the certainty basically is 0 as expected, but the bipartition-based IC score can give artificially high IC scores. And we also introduced arrows in the reference tree. So basically, if our reference tree is inaccurate, how would the IC measures perform? So again, the IC-based IC scores at high, bipartition-based IC measures at high level of missing data can give rise to artificially high IC scores. But the Quartet-based ones, particularly the EQP IC approach, would tend to give a negative IC score for those incorrect branches, which is matched with our expectation. So here basically summarize the performance of different bipartition-based IC scores and Quartet-based IC scores under different conditions. Although we have developed 3 different flavors of Quartet-based IC scores, the one we actually recommend is the EQP IC. You can see that it's robust to missing data, missing taxa, lack of signal, and errors in the tree, every condition that we have tested. And when we applied different IC scores to many different phylogenetic datasets, you can see that in a lot of datasets, there are still pretty high level of phylogenetic incongruence. Although the LPP support from the Astral, which is a popular approach for making species trees, is nearly perfect for a lot of those branches. But when you look at underlying gene trees, there are still a lot of incongruence. This approach has been implemented in a program called Quartet Scores. So if you're interested in applying this approach on your dataset, you can easily go to the GitHub page and download, and it's easy to compile and easy to use. In the end, I would this work, make some acknowledgements. This work was finished after I returned to China and joined my current institution, the South China Agricultural University. But it was started when I was doing my postdoc at Vanderbilt in Antonius Rokas lab. So a lot of thanks to Antonius and all the members of the Rokas lab, and a special thanks to Sarah, Lucas, and Alexis for the highly efficient implementation of the algorithm in the Quartet Scores program. And that's the end of my talk. And thanks for listening. And I will be happy to take any questions.
Thank you very much. Thank you very much. We already have one question. We are really tight on time, so we are just going to formulate this question and move to the next session. Thank you very much. It's by Robson Francisco de Souza that asks, could you extend the EQP IC even further by considering all paths connected to internal nodes? Would such an extension require further corrections?
How about if I reply that on Slack? I think by writing it down, it's probably easier for us to understand how it works.
Fantastic, fantastic. Thank you very much again.
Thank you.
So we are going to move to the